Hello everyone. My name is Sarah Omoike. I'm a software engineer, uh, all the way from Lagos, Nigeria, West Africa. So we are one of the partners for the Notes 2020, and I am super excited to be part of this conference. I've learned so much, and I look forward to learning more. So just a snippet of who we are. Lagos Supply MLDS is the global community, global chapter for, local chapter for the global WMSDS community. We are an inclusive community for underrepresented persons in data science, machine learning, and artificial intelligence. Our URL is on the screen. You could check us out and see more on who we are and what we are about, our mission, and all the other details. You can also tweet at us. Our handle is at WMLDS_Lagos. We would be more than happy to receive your tweets. So coming up next is Estelle. Next session is extending the knowledge graph from Wikidata. Presenter is Estelle Scifo, a data scientist. Estelle Scifo is a data scientist entered into the field from physics, hobbies, Python, and React developer, graph and Neo4j lover. Estelle is a creator and maintainer of NeoMap. NeoMap is Neo4j desktop application to visualize spatial data, and the author of Exploring Graph Algorithms with Neo4j video and Hands-on Graph Analytics with Neo4j book via Pact Publishing. This looks like a very exciting session, and I also look forward to learning a lot. Can we have Estelle up, please? Thank you.
Hello everyone, so I'm really happy to be with you today. So my talk is about extending a knowledge graph from Wikidata. So before starting, a few words about me. So I'm physicist by education turned data scientist turned graphista. I am the author of several Neo4j related contents, from blog posts that you can find on Medium or toward data science, to a video course related to graph algorithm. And the newly born in this series of content is a book called Hands-on Graph Analytics with Neo4j. And if you stay until the end of this talk, you'll get a discount code for this book. If you want to, you can also follow me on Twitter with the @Stellasia handle. Before continuing, I just want to add a disclaimer that despite I will talk about Wikidata and Neo4j in this talk, I'm not affiliated to neither of these organization or company. I'm just an enthusiastic user of both these technologies. So in this talk, I'll start with a quite long introduction to Wikidata and its query language, which is called SparkQL. Then I will present the initial graph model that I will use in this presentation, which is related to a bookstore. Then I will show you how we can import Wikidata information into Neo4j to add more information in the graph. And finally, we will review some of the applications we can build using this new data. If you have any question during the talk, please use the chat. I do my best to answer the questions at the end of this talk. So let's get started and dive into Wikidata and its query language. So Wikidata, for those who don't know, is part of the Wikimedia family, related to Wikipedia, Wikimedia Commons for images, or Wiktionary, for instance. It was created back in 2006, and its first contributions were in 2012. From 2020, actually, they have more than 12,000 contributions with several tens of millions of items, and also many languages are covered. So Wikidata, you can access it via wikidata.org webpage. It describes itself as a free and open knowledge base that can be read and edited by both humans and machines. And indeed, if you try to go to wikidata.org, they have a search engine that allow you to search for different entities that are present on Wikidata. For instance, on this slide, you can see a screenshot of the top of the page of the Wikidata page itself. If you scroll down, you will see different types of content, from text to images showing, for instance, logos, to audio file for the pronunciation of the different names. On this page, you can also see different entities that will be useful for us. First of all, if you check the URL of the page, you will see that it ends with an identifier, which is Q2013, which is the identifier for Wikidata, and we will use it a lot through this presentation. You can also see different type of statements that in the Neo4j world will be translated as relationship type. For instance, you can see that Wikidata is part of the semantic web. So semantic web has been something very popular during the last years. The goal is to extend the web as we know it today to facilitate data exchange and make data more consistent among all different sources and websites. If you browse a little bit Wikidata, you will see that the range of covered topics is really huge, like Wikidata or other Wikimedia related content. You will find entities related to culture, sports. You can find information about food and your favorite dish, your favorite technology, or your favorite historical person. Since it's also integrated with Wiktionary, you also have information about words such as chair, brush, or knife. On top of entities, the power of Wikidata is that it also contains different types of relationships. So it will contain temporal data, such as anniversary or release dates, spatial data, such as a city, which is part of a given county, which itself is also part of the state in a country. And we also have seen, for instance, in the Wikidata screenshots in the previous slides, that we have some composition, relationship, and many, many more, as we will see during this talk. So this part was mainly for human. Let's talk about Wikidata for machines. Wikidata is said to be also for machines, since it can be queried through, for instance, the Wikidata query service. So if you go to query.wikidata.org, you will see a textorial looking like this one, asking you to input some SparkQL query. In the following, we will go a bit deeper into SparkQL and learn how to build a query to retrieve a certain type of information. So SparkQL is a query language for the RDF data format, which is basically based on the following structure. It's a triplet based on a subject, a predicate, and an object. In this slide, I have intentionally added the parentheses to match what we are used to see with Neo4j, with the brackets showing the nodes and the square bracket showing the relationship. So here the predicate is basically the verb or the relationship connecting two components. For instance, if we want to know which services are using Wikidata that correspond to the screenshot on the right of this slide, we will write the following SparkQL query, where the WDQ2013 is the identifier for Wikidata, as we noticed earlier in the URL. WDT-P1535 is the identifier for the predicate used by. And finally, we end the query with a question mark, other, which is the name of the variable that we want to see. In terms of cipher, if we had to write the same query, it would be something like match Wikidata, then the relationship used by, and we are missing here the final row in the relationship, but the arrow target is the other node that will be returned. If you run this query into the SparkQL query builder, you will see a result looking like the one on the bottom of this slide. So only showing basically identifiers for the tools that are used by that are using Wikidata. So that's not really readable, and we're going to enhance the above query to add the labels and to add something that is human readable. If we want to extract the labels in English, basically we have to add a service to our query saying Wikidata that we want to extract the labels in English, and then we just have to access on top of the other variable, the question mark other, we can add a question mark other label. And the result of this query is also displayed on the table at the bottom of this slide, and you can see that on top of the identifier for the other entity, we also have their labels, which are much more readable and much more useful. A bit more on this query tool. So on the previous slide, you had the graph view, the table view, sorry, and here you have an example of how the graph view looks like. And it's also interesting because, for instance, if you click on one of the nodes, such as Open Refine, you end up with an extension of the graph, such that you can also do with Neo4j browser, where some of the relationships related to Open Refine are extended. So you can, for instance, see that the license used by Open Refine is a BSD license. So let's go a bit deeper into SparkQL and investigate some distance queries. For instance, we might ask, what are the 5 metro stations closest to the Sagrada Familia in Barcelona? This can be done with a bit more complex query compared to the one we have seen before, which basically consists in selecting the entity which is located in the administrative territorial entity Barcelona. So that's what the blue part of the query means. Then we also want this entity to be an instance of a metro station, which is the yellow part of the query. And from this entity, so these entities that match the 2 requirements, we will extract the coordinates. Then we also need to have an information about the starting point, so the Sagrada Familia itself, which is this identifier 43435. And from this information, we can basically compute the distance between the 2 coordinates, which is the green part of this line. Then we can, as we would do with normal SQL or with Scifo, we can order the result by distance and limit the result to 5. So if we run this query, you will see the following result, where the metro station closest to the Sagrada Familia is called Sagrada Familia, and then you have quite a few less than 1 kilometer away from the basilica. Here, something that is still annoying is that you have to know the identifier for each of the entity you want to use. For instance, if I'm not saying you that WDQ483435 is the identifier for the Sagrada Familia, you wouldn't understand what this query is about. But happily, actually, we can try and match the entities based on their label. For instance, the SparkQL query on this slide will match the entity whose label in English is Wikidata. So With this in mind, we can rewrite the query we wrote earlier to extract the entities using Wikidata with something a bit more readable, where we will just say, okay, the variable wiki is the one with the label Wikidata. And then from this variable, we want to extract the entities that are related to it through the predicates used by. So the last two queries on this slide are totally equivalent and will yield the exact same result. Only the second one, the bottom one, is a bit more readable. Such about label, we can do the same, for instance, using Barcelona as label. And if you run this query here, where we have just replaced basically the word Wikidata by Barcelona, you will see that we have many different results. So many of them actually are not related to the Barcelona we're talking about in Spain. So you'll see that there is a city in Venezuela called Barcelona, another one in Philippines, some village in Ukraine, and there is even an album from Freddie Mercury, and many more results that are not the city we are interested in Spain. So we will try to narrow down the result by adding more constraints on our selection. For instance, we can look for the city whose label is Barcelona, which is an instance of big city. So far, we have not added any information about the type of entity we are looking for. Here we are asking for the matched entity to be a big city and to be located in Spain. So that's basically what this query here is doing, where we select the country named Spain, then we select an entity called Barcelona. We ask explicitly for this entity to be in Spain, and finally we ask that this entity is an instance of big city. With this query, we get the only city we are interested in, which is the Barcelona of Spain. With the same principle, we can rewrite the query we wrote earlier regarding the number of the metro station close to the Sagrada Familia in Barcelona. And for instance, get the Spain, which is the Spain country. We get Barcelona and we get the Sagrada Familia, and it's the same ID. If we only request Sagrada Familia based on label, we will have many, many different results. And we have to narrow down the number of entities, asking, for instance, for it to be in Spain, to be a tourist attraction. And then we can get the only entity we're interested in. So if you check again the web page, so the Wikidata query service, you will see that if you click on the code on the next to the results, you can get some hint about how to query Wikidata from different languages. Here I will just stop on the first one, which is the URL, because we are going to use the API and call this API from Scifo. So the endpoint is only query.wikidata.org/SparkQL. And we have one mandatory parameter, which is the SparkQL query we want to run. And there is an optional parameter that I'm going to use because the default written format is XML, and I will just force the format to be JSON. That's only a personal choice because I'm more comfortable with JSON with respect to XML, but you are totally free to use XML if you want to. So on the right here, you can see an example of written JSON for the entities using Wikidata. And you can see that the value of interest is located inside the results.bindings.other.value. And here we have only the URL of the entity. So now we have a better understanding about how we can build a SparkQL query and how we can query Wikidata. Let me introduce the graph model we are going to use, before we can understand what kind of information we can add to it. So the context here is a bookstore. So my graph, my Neo4j graph, actually contains for each book, which are the blue nodes on this slide, title and the release date. And each book is connected to its author and has at least one category. So category are the yellow nodes here, while the author are the red nodes. So the graph I'm using for this demonstration is quite small. So most of the queries we are going to run will be very fast. So given that we have authors and books, what kind of information can we add from Wikidata? So we can go to the page for an author such as Tolkien, for instance, and check what are the different statements that are available. Here I give another option, which is to use a SparkQL query to list all of these statements. So you can see that from Tolkien, you can get many different information from its family name to its parents, its military rank, academic degree. You have the prizes he received or not, the prizes he was nominated for, etc., etc. So in this talk, I will focus on several of these categories and try to retrieve the information related to each author, writing, and native languages, the place and the date of birth, together with the genre and the award received. And finally, we will also retrieve the information of the influence, which actually lists some other authors that influenced our author. So that will help us create some relationship between authors, and we will see some application of this new kind of data at the end of this talk. So if we want to retrieve, for instance, influencers, the SparkQL query will be something like this. So we have the author, whose label is something like Tolkien, and then we follow the relationship of type influenced by and retrieve the matching object, which is the influencer, and then we retrieve the influencer label in English. So that's the kind of information we can retrieve and we will retrieve from Wikidata. Now let's see how we will do that from Neo4j. So in this talk, actually, I will use APOC, which is an extension for Scifo, and contains many procedures and functions that will help us doing many things. And here, I'm mainly interested in the APOC load JSON param procedure that will call an API with given headers and parameters if needed, and return the results as JSON. So for instance, let's use it with a simple query that we used at the beginning, which is which services are using Wikidata. So the query is very simple. This is the first row of this Scifo query, where the string contains the SparkQL query. Then we call the procedure, the APOC procedure, by building the URL. So the URL is basically query.wikidata.org/SparkQL, the format JSON for APOC to parse it, and finally the query with the URL encoded SparkQL query. APOC is returning one value that we are going to study right now. So you can see that it actually contains the exact same JSON that the API, the Wikidata API was returning, which is normal. And our value of interest, so the information we want to retrieve, is still located inside results, bindings, and other, because other is the name of the column we used. So what if we want to retrieve the writing language for each of our authors? First of all, we will have to match our authors, so extract our author node from our graph. Then we will have to build the SparkQL query. And here we will have to inject the author name inside the query. From this query, we will call the Wikidata API using APOC. Finally, we'll have to extract the results, extract the data from the results, and create the nodes and the relationships that are missing in our graph from this data. So the SparkQL query to extract the writing languages is this one. So very similar, very simple query, very similar to the one we have seen so far. And in order to use it inside a Scifo query, we will start by matching all authors in our database. So as I mentioned earlier, the graph I'm using right now is quite small, so there will not be any problem in running this query, and we will be able to query the API, the Wikidata API for each of our nodes without any trouble. So with this author, we can build the SparkQL query where we inject the name inside the query as author label. Then we build the URL to query the Wikidata API. And finally, we can parse the results. So as we have already seen earlier, the value we want to retrieve is in the map results bindings. So bindings is actually an array. So here I'm considering only the first writing language, considering that author mainly have only one writing language. And I'm retrieving the value for this language. Once this is done, I create or I retrieve the node with type language and whose name is the value I just retrieved. And I create the relationship between the author and this language. If we try and do the same for influencers, there can be several influencers per author, and most of the time you will have several values, and it makes no sense to select only one, or it will be a pity. So we will see how we can do basically the same, but create all the relationships for all the influencers. So here the query is very similar. The only difference is the use of the unwind Scifo keyword, where each of the values in the bindings part are actually exploded, and for each of these values or each of these influencer, we create the author node if it doesn't exist, and we create the relationship between the initial author and this new node. Actually, the resulting graph is also shown on this graph, on this slide, where you can see that we have many new nodes that are not connected to anyone, and a few of them, such as here, Stephen King, are related to J.K. Rowling or Edgar Allan Poe. So let's go ahead and talk about the applications of this new kind of data. So as a reminder, we have now in our graph books, authors. We also have languages. We have a release date for books, and we have a relationship of influence between authors. So what can we do with this data? We can use this data to have a better categorization of the author or the books themselves. We can use it to build some recommendation, and we can also use this data to enhance a search engine. So to build some categorization or recommendation, we can build some author communities. So since our authors are connected to each other through an influence relationship, we can use a graph algorithm implemented in the graph data science library to find author communities, so authors that interact together more often than others. Here you have an example of a Scifo query called the Louvain algorithm from the GGS, and writes actually the result into a Louvain property for each of the author nodes. The result of this categorization is also shown on the slide. So this graph is quite simple and quite straightforward, I would say. So there is no special problem with this, and you can see that most of the communities that we expect are properly identified. The question now is, okay, good, we have some author communities, and now what? Well, now we can use this information to provide some recommendation to users. So imagine that we have also in our graph some users and the information about which books they have actually purchased or read. Then we can just extract the author that the user is reading, find the other author in the same community that have the same influence, and also propose to this user this author or the books written by this author. Since we can expect the style, the writing style, or the topics to be similar. That's exactly what this query is doing. The first line you see is basically getting the name or the author node whose book has been read by a given user, and then we extract the other author that have the same community, the same Louvain community as the A author. And finally, we extract the books that have been written by this other author and that have not been read by our user yet. So that's a kind of recommendation we can make. If we run this query, for instance, on our graph, that's the example of result we get. So user 1 has read It, that was written by Stephen King. Stephen King also wrote other books that apparently were not read by this user, that we can obviously recommend. But you also see that Stephen King was influenced by Ray Bradbury, and maybe some of the books written by this author can also be a good recommendations for this user. This, of course, can be enhanced by using the categories or other information that we have in our graph. That's an example. Another application is the search engine. So how do you search into a database? There are different kinds of search, such as, for instance, keyword-based, where basically you will retrieve all books with a given keyword or a given category. So all books in category fiction, for instance, that's one way of searching. You can use a full text search, for instance, where you will try to match books whose title contain a given word, such as man. But then you can go into more complex type of search. Here I show you the definition that Facebook gave of graph search when they introduced this feature on their social network a few years ago. And the idea that you can ask very simple questions, such as give me the friends, my friends who live in San Francisco, or show me the photos of my family taken in Copenhagen. And the engine should be able to answer that kind of question. And that's doable with a graph and a graph database especially. Let's see a few examples. For instance, with our new enriched database, we can get the information about the science fiction books that were written before the 50s and in English. How can we do that? Well, we first get the books that are into the science fiction category. Then we can also find the book's author and the language this author is using. And finally, we can filter on the release date of the book and ask it to be before the 50s. That's one example of how a graph can help in building and answering very precise questions. Another example in the same kind of application is, okay, now I want the horror books written by American women. And you can do basically the same, starting from books in a given category, but you can go much deeper and finding the author that are born in a given country and with a genre which are female. So that's basically the example I wanted to show you. We can go even further because in this talk I have only extended the information related to the author, but we can do the same for the books. And if you check what kind of information is available for the books on Wikidata, you will see that you will have the information about the book series or the order an author wrote his book, the main characters inside the book, or even where the story takes place. So we can find stories in London or in New York, or inside the books from Agatha Christie, we can extract the one involving Miss Marple, for instance. Another very interesting topic is if you have really a big database and want to import much more information from Wikidata. So here I had only a couple of books of authors, and I queried basically the Wikidata API once per author. But we can also imagine if you have many of them that you want to import into your database a whole bunch of information from Wikidata. And that's one of the features of the Neo4j plugin called Neo-Semantics. So there are different talks today about it, and you can check the documentation and the different content about it and see how it can be used to import the whole Wikidata or whole part of Wikidata into your graph. So on top of Neo-Semantics, you can find here some other references related to the semantic web or Neo4j and knowledge graphs. Thank you very much for listening.